Hello, welcome to another module in this massive open online course. So, we are looking at examples on matrices and also convex sets. So, let us continue our discussion. Let us look at another example related to positive definite matrices. Alright, so let us continue our discussion or continue looking at examples related to matrices and convex sets. So, this example number 3, what we want to show that is A is a PD matrix, that is positive definite if A is positive definite, this implies A inverse is also positive definite. Okay. We want to show that if A is positive definite, A inverse is also positive definite. This can be shown as follows. If A can be written expressed as, we have already seen this, U lambda U Hermitian, where U is a unitary matrix, satisfies U Hermitian equals U Hermitian U equals identity, and lambda is the diagonal matrix of eigenvalues. And also further, we have seen that the eigenvalues of any positive definite matrix have to be greater than 0. The eigenvalues of a positive semi definite matrix are greater than or equal to 0. The eigenvalues of a positive definite matrix, they have to be strictly greater than 0. It cannot have any eigenvalues equal to 0. And therefore, now if you look at A inverse, it is rather easy to see A inverse equals U lambda U lambda U Hermitian inverse, which is basically U Hermitian inverse times lambda inverse times U inverse. But we have seen that U is a unitary matrix, which implies U Hermitian U equals U Hermitian equals identity. Well, this implies U equals U Hermitian. So, what this implies is that if you look at U Hermitian inverse, that is U itself, because U Hermitian into U's identity, times lambda inverse into U inverse is U Hermitian, because again U Hermitian equals identity. And therefore, this is again has the same structure, except you can see with eigenvalues 1 over lambda 1, 1 over lambda 2, 1 over lambda n times U Hermitian. And therefore, now you can see if lambda I is greater than 0, this also implies that 1 over lambda I is greater than 0. So, the eigenvalues of A inverse are also greater than 0, and in fact, A inverse can be expressed as U lambda inverse U Hermitian, and therefore, it has positive eigenvalues, alright, and therefore, it is also a positive definite matrix. And you can also check this as follows. For instance, if we consider Z bar transpose for any real vector, if you consider Z bar transpose A inverse Z bar, I can now write this as, now since this is a real vector, I can write this as Z bar Hermitian. A inverse we have seen is U lambda inverse U Hermitian Z bar. Now, if we set U Hermitian Z bar, if we set this is equal to Z tilde, then this will become Z tilde Hermitian lambda inverse Z tilde, which is equal to Z tilde 1, Z tilde 2, so on up to Z tilde n into the product 1 over lambda 1, 1 over lambda 2, so on 1 over lambda n times Z tilde 1, Z tilde 2 up to Z tilde n. And if you look at this, this is nothing but, well, this will be Z tilde I conjugate, since this is the Hermitian of the vector. Okay, so we are setting U Hermitian Z bar Z tilde. So this will be summation over I equals 1 to n 1 over lambda I Z tilde I conjugate into Z tilde I, that is magnitude Z tilde I square. Now 1 over lambda I, this is greater than 0, magnitude Z tilde I square, this is greater than 0, and therefore this implies that Z bar transpose A inverse Z bar is also greater than 0 for all Z bar, for all vectors Z bar, and this implies that A inverse is a positive definite matrix. So if A is a positive definite matrix, A inverse is also a positive definite matrix. In fact, the eigenvalues of A inverse are the inverse, that is, if lambda is an eigenvalue of A, then the eigenvalue of corresponding eigenvalue of A inverse is 1 over lambda I. Eigenvalues of A are strictly greater than 0 if A is a positive definite matrix, and similarly the eigenvalues of A inverse are also strictly greater than 0 if strictly greater than 0, correct. Since lambda is greater than 0, 1 over lambda I is also greater than 0. Okay. All right. Let us continue our discussion. Let us look at another problem, example number 4. What we want to show is that if A comma B these are two invertible n cross n matrices, then AB comma BA have the same AB and BA have the same eigenvalues. We want to show this property, that AB, eigenvalues of AB are equal to the eigenvalues of BA. Well, we start with the characteristic polynomial. Remember, to compute the eigenvalues of any matrix, in this case the eigenvalues of the matrix AB, so we will start with the characteristic polynomial of AB, that is obtained by nothing but, that is basically obtained by looking at the determinant of AB minus lambda I. Remember, the eigenvalues are computed as the roots of the characteristic polynomial. The characteristic polynomial of a matrix A is A minus lambda I. We want to look at the characteristic polynomial of the matrix AB. Therefore, that will be the determinant of AB minus lambda I. So, this is equal to, I can write this as determinant of AB A inverse minus lambda A inverse. because remember A is an invertible matrix, both A and B are invertible matrices. So, A inverse equals identity. So, I can always write this as AB, determinant of AB, A inverse minus lambda A inverse. Now, I can extract the A on the right. So, this will become BA minus lambda I times A inverse. This is the determinant of A times BA minus lambda I times A inverse. The determinant of a matrix product is the product of the determinants, that is determinant of A times determinant of BA minus lambda I times determinant of A inverse. Determinant of A inverse is basically 1 over the determinant of A, because A times A inverse is identity. So, this is BA minus lambda I into 1 over the determinant of A. Determinant of A times 1 over determinant of A, these cancel. So, this becomes the determinant of BA minus lambda I. Therefore, we have this interesting property, that is AB, determinant of AB minus lambda I equals determinant of BA minus lambda I, implies characteristic polynomials of BA. This implies the characteristic polynomial, of AB, which is determinant of AB minus lambda I. This equals the characteristic polynomial of BA. Okay, the characteristic polynomial of AB equals the characteristic polynomial of BA. This implies the roots are equal, or identical, and this implies, so the characteristic polynomials are equal implies the roots are identical, and this implies therefore eigenvalues of AB equal eigenvalues of, this implies eigenvalues of AB equals this implies that eigenvalues of AB equal eigenvalues of BA. Okay. And in fact, you can see if you write AB equals U lambda U inverse, remember this is eigenvalue decomposition, I can write, since their eigenvalues are equal, I can write BA equals some V times lambda times V inverse, because remember their eigenvalues are equal. So, the diagonal matrix of eigenvalues will be the equal or identical similar eigenvalues, they have the same eigenvalues. Since they have the same eigenvalues, the diagonal matrix is lambda, right, the diagonal matrix of eigenvalues will be the same for both AB and BA in their eigenvalue decomposition. Okay. So, now this implies that BA equals V lambda V inverse. So, this implies V times or V inverse times BA into V equals lambda. Now, substitute lambda in the first one, this implies AB equals U times lambda, but lambda is V inverse BA into U inverse V, and this is nothing but UV inverse, let us call this as U tilde BA. If U inverse UV inverse is U tilde, then U inverse B becomes U tilde inverse. So, I can write the matrix AB as some matrix U tilde, I can write this as U tilde times BA times U tilde inverse, such matrices are said to be similar matrices. So, AB implies AB is similar to BA. In general, C is similar to D if there exists M such that C equals M inverse D M. So, if there exists a matrix M such that you can write C equals M inverse D into M, then the matrices C and D are said to be similar matrices. So, in this case you can see these two matrices AB and BA, in fact, which have the same eigenvalues, alright, these are similar matrices. Okay, alright. Let us now look at another interesting property, that is the eigenvalues of a unitary matrix. So, this is our example number 5, again another simple property. What can we say about the eigenvalues of a unitary matrix? Now, let U be a unitary matrix. Remember, the unitary matrix is defined by the property U Hermitian U equals UU Hermitian equals identity. This is the property of the unitary matrix. Now, let x bar be the eigenvector, and lambda equals corresponding eigenvalue. Now, this implies, what this implies is that Ux bar equals lambda times x bar, correct, which implies, now if I multiply Ux bar Hermitian Ux bar, that will be equal to lambda x bar Hermitian, because Ux bar equals lambda x bar, Ux bar Hermitian equals lambda x bar Hermitian multiplied by lambda x bar, and this implies x bar Hermitian U Hermitian U x bar equals lambda Hermitian, but lambda is a number. So, lambda Hermitian is simply lambda conjugate x bar Hermitian lambda into x bar. Now, U Hermitian U is identity, because U is a unitary matrix, that leaves x bar Hermitian x bar, which is, remember, norm of x bar square. This is equal to lambda conjugate lambda, that is magnitude lambda square, times x bar Hermitian x bar, which is again once again norm x bar square, which implies, cancelling the norm x bar square on both sides, this implies magnitude lambda square equals 1, which means magnitude lambda equals 1. So, this implies basically that so this basically shows a very interesting property, eigenvalues of unitary matrix eigenvalues of a unitary matrix have unit magnitude. That is the interesting property that this shows, alright. And now, similarly, if you consider the determinant of a unit, the magnitude of the determinant, let us consider the magnitude of the determinant. Remember, we have seen that the determinant is nothing but the product of the eigenvalues. So, the magnitude of the product of the eigenvalues, which is nothing but the product of the magnitudes of the eigenvalues. And each eigenvalue is unit magnitude. So, this is equal to the product of ones, which is 1, which shows this ancillary property, or you can also think of this as an axiom, that the determinant of a unitary matrix is identity. All the eigenvalues of a unitary matrix have magnitude 1, and the determinant of a unitary matrix has the magnitude of the determinant of a unitary matrix is 1 as well. Okay. All right. Let us continue our discussion. Let us start with another example. Let us consider the norm, the relation between the one norm of a vector. We want to show that the one norm of vector x bar is less than or equal to square root of n times the 2 norm. Now, if x bar is a vector with elements x1, x2 up to xn, now remember the one norm this is simply the sum of the magnitudes, the magnitude of magnitude x1 plus magnitude x2 magnitude xn, and the 2 norm is the square root of magnitude x1 square plus magnitude x2 square plus so on plus magnitude xn square. Now, to show the property above, what we will do is we will consider two different vectors. We will construct two vectors u bar n components. The elements of u bar are magnitude x1, magnitude x2. So, I am constructing two different vectors, magnitude x1, magnitude x2, so on magnitude xn, and v bar is the vector, n dimensional vector of all ones. Now, what I am going to do is I am going to apply the Cauchy-Squartz inequality. Remember, we have seen the Cauchy-Squartz inequality, which states that the inner product square u bar v bar, that is less than u bar, that is norm u bar square into norm v bar square. This implies that if you look at u bar transpose v bar square, that is less than or equal to norm u bar square norm v bar square, and this also implies that u bar transpose v bar is less than or equal to norm u bar into norm v bar. We know this property. Now, all we have to do is substitute the definition from the definition above, substitute u bar and v bar. You can see u bar transpose v bar is nothing but magnitude x1 plus magnitude x2 so on up to magnitude xn, which is basically norm x bar of 1, and norm u bar, that is the 2 norm. Remember, the 2 norm of u bar is square root of, well, magnitude x1 square plus so on magnitude xn square, which is nothing but the 2 norm of x bar, and finally the 2 norm L2 norm of v bar is square root of, this is 1 plus 1 plus 1 n times, this is nothing but square root of n. And now, using this property, using 1, substituting all these in 1, this basically yields norm x bar 1, that is u transpose v bar, less than or equal to norm v bar, that is square root of n, into norm u bar, that is the 2 norm of x bar. So, this is an interesting property that we have. Okay. So, this is the property, or the relation, you can say, characterizes the relation between the 1 norm and the 2 norm. In fact, you can also show something between the relation between the 2 norm and the infinity norm. You can also show that the infinity norm, that is, if you look at the 2 norm, now this is equal to, well, we have seen magnitude x 1 square plus magnitude x 2 square plus magnitude x n square. This is the sum of the squares of the magnitudes of all the elements. Now, this is greater than or equal to, you simply take the maximum of the magnitude correct. This is the sum of the squares of the magnitudes of all the elements, which is greater than or equal to the square of simply the magnitude of the maximum of these elements, which is equal to, now if you take the square root, all you are left with is the maximum of magnitude xi, which is nothing but the L infinity norm. Okay. So, therefore, this shows that basically your this thing is greater than or equal to the L2 norm is great. So, this basically shows that your L2 norm is greater than or equal to the L infinity norm. Okay. All right. So, let us stop here and we will continue with other aspects in the subsequent modules. Thank you very much.